Hello everyone. In this video, we're going to explore how we can evaluate limits algebraically. So the first thing to note is if I have a continuous function, then the limit of the function at a particular value of x is actually going to be the value of that function at that value of x. So here's the notation: the limit as x approaches 1, for example, of x squared plus x plus 3. Now we know that that's just a quadratic function. It's a parabola. It's continuous everywhere. It has no breaks or gaps or anything. So what that means is that the limit of the function as x approaches 1 has to actually be the value of the function when x equals 1. So all we have to do to find it is simply substitute in 1. So this is our very first step every single time. It's going to be 1 squared plus 1 plus 3. Our first step is to actually substitute in the value that we're given and see if we can find a number that way. So in this case, when I do that, 1 plus 1 plus 3 is 5. So the limit of this function as x approaches 1 is 5. Now, that is also the value of the function when x is 1. But in a lot of cases where we don't have continuous functions, this process won't work. But that should always be the first check that you do. Can I simply substitute in the value that is given and find a number? If I can, great, there's my limit. If I can't, that's where I have to do some manipulations. So if I look at this next example, the limit as x approaches 2 of the rational function x squared minus 4 over x minus 2, well, 2 is a non-permissible value here. That is not necessarily in and of itself an indicator that that I can't simply do a substitution and kind of reason my way through, but we end up with a few different what are called indeterminate forms. So what happens if I substitute 2 in here is not only do I get 2 in the denominator, that's pretty obvious, 2 minus 2 is 0, or sorry, I get 0 in the denominator, but I also get 0 in the numerator. 0 minus, or 2 squared minus 4 is also 0. This is an indeterminate form. If I had some non-zero number in the numerator, which is what we'll see in our next example, then I could reason my way through this. But the problem with why this form is indeterminate, 0 divided by 0 is impossible. I can't actually do that calculation. But I don't actually have 0 divided by 0 here because I'm not talking about values that actually are equal to 2. I'm just talking about values that are close to 2. So x isn't 2 exactly. X is maybe 1.999, in which case my numerator isn't exactly 0 and my denominator isn't exactly 0, but it is some value close to that. So the ratio of those two numbers might be something very definite, and that in this case it actually is. So I need some other way of kind of figuring this out. Now, we learned before that when we're dealing with rational functions, rational expressions, we can often simplify them by factoring. So one of our next steps, if I can't simply substitute or I end up with an indeterminate form when I do substitute, is to see if I can simplify that expression using the algebra that we've learned in previous math courses. One of the first steps should be to check if it's factorable. In this case, it is factorable, which means that this expression is actually equivalent to the expression just x plus 2 for values of x that aren't 2. But the nice thing here is I'm dealing with a limit as x approaches 2, so I don't have x equals 2. I have x as some non-2 value, close to 2, but not 2. So in these cases, these two limits are equal. The limit as x approaches 2 of x squared minus 4 over x minus 2 is equal to the limit as x approaches 2 of x plus 2, because those two expressions, x squared minus 4 over x minus 2 and x plus 2, are equivalent for every value of x except 2. And 2 is not the value of x that we have here. Now, in order to find the limit, I actually do substitute in 2. So this is simply 2 plus 2, which is 4. So this limit is equal to 4. What that means, based on what you learned before, this is a point of discontinuity. If I'm drawing this rational expression, it's equivalent to the line x plus 2, the line y equals x plus 2, with the exception that it has a hole in it at the point 2, 4. So that's graphically what this means. Algebraically, if I can factor and simplify and then substitute in the value I'm looking for, I can figure out what the limit would be. In this next case, that isn't quite what happens because this rational expression can't be factored or simplified. It is in its simplified form, x plus 7 over x minus 3. And we do have that non-permissible value of 3. But what happens here, if I substitute in 3 into the numerator, I get 10. And into the denominator, I get 0. This is actually not quite an indeterminate form. I can reason my way through this one because my numerator is 10. And my denominator, now notice, this isn't just the limit as x approaches 3. This is the limit as x approaches 3 from the positive side. In other words, x is some number that isn't 3 but is very close to 3 but is slightly bigger than 3. So not only, I don't have a 0 in the denominator, I have a number that is very, very close to 0 but slightly positive because I've taken a value that was a little bit bigger than 3 and I've subtracted 3. So 3.0001, for example, minus 3 is 0.0001. So it is a number that is close to 0, but it is still slightly positive, and that is important because now what I'm thinking is I'm not dividing 10 by 0. I can't divide 10 by 0, but I'm dividing 10 by a very, very, very tiny but still positive number. Now, the smaller the number in the denominator is, the larger the overall quotient will be. So 10 divided by an incredibly tiny number gives me an incredibly large number. So this actually doesn't have a limit. There's two appropriate ways to answer this question. This expression, 10 divided by a very tiny but still positive number, goes to infinity. It gets larger and larger and larger. Infinity, by definition, is not a limit. If infinity is limitless. So it is entirely appropriate here to say that the limit does not exist, which is a correct answer. It's, I believe, what most of the textbooks say. So the notation for that does not exist. It is also, though, entirely appropriate and maybe a little more useful to say the limit as x approaches 3 from the positive side of x plus 7 over x minus 3. Now, I can't say equals because it doesn't equal anything, but I can say goes to infinity, goes to positive infinity. The reason that's a little more helpful is because graphically that helps me understand a little better what's going on. What I understand as soon as I see the infinity is that I'm dealing with an asymptote, because asymptotes are about what's happening at infinity. But it's telling me that graphically this function is going up as opposed to, say, going down. That's what I would have if it was going to negative infinity. So it does tell me a little something about the behavior of that function around that asymptote if I say that this limit is going to positive infinity. Like I said, though, when all we're dealing with is the algebraic limits, it's entirely appropriate and correct to say the limit does not exist. But to think through, okay, but the limit is approaching infinity. You cannot write equals infinity. And please be very careful that you are using limit notation correctly. So notice here in the first example, once I substituted in the number 1, I no longer had a limit. I was actually calculating what it equaled to, so I don't need to write the limit anymore. But in the second example, when all I was doing was simplifying the expression, I'm still dealing with a limit. That the limit as x approaches 2 of that first expression is equal to the limit as x approaches 2 of the second expression. And then once I substitute in the value of x, I drop the limit notation. I'm just calculating the number. All right, let's look at a few more. So some cases where we can factor and some cases where we can't. So in this first example, again, always check, do you actually have an indeterminate form if you substitute in? So in this case, if I were to substitute in 3 cubed minus 27 is 0, 3 minus 3 is 0. This is an indeterminate form, so I can't just reason my way through like I did in the previous example. But I can factor because I have a difference of cubes in the numerator, which factors to x minus 3 times x squared plus 3x plus 9. Which means that because the x minus 3's will cancel, this is equivalent to the limit as x approaches 3. I still have an algebraic expression here, so I still have a limit notation of x squared plus 3x plus 9, which means actually that the original rational expression is equivalent to the parabola that I now have, y equals x squared plus 3x plus 9, if I were to graph it, but it's going to have a hole in it when x equals 3. And in order to figure out where that hole is going to be, I can now substitute 3 into this. So 3 squared plus 3 times 3 plus 9, which is 9 plus 9 plus 9, which is 27. So the limit as x approaches 3 of x cubed minus 27 over x minus 3 is 27. Or in other words, the point of discontinuity would be the point 327. In the next example, I can't factor though. So I have to find other ways of dealing with this. And one of the other algebra tricks that you've learned is rationalizing or multiplying by a rational conjugate. Usually we've done that to rationalize the denominator, but I can rationalize the numerator as well. I should start with my first step, though, of double checking that I do in fact get an indeterminate form. The denominator is obviously going to be 0 if I substitute in -1. -1 plus 1 is 0. The numerator, -1 plus 2 is 1. The square root of 1 minus 1 is 0. So I do have an indeterminate form. So I'm going to do some algebraic manipulation of this fraction. So the square root of x plus 2 minus 1 over x plus 1. What I am going to do is I'm going to multiply by the conjugate of the numerator. So I'm kind of rationalizing the numerator just to get a manipulation happening here to see if I can get an alternate form where I can substitute in. In other words, where I don't have x plus 1 in the denominator. So if I distribute the numerator, I get x plus 2 minus 1 squared, which is just minus 1. In the denominator, I'm not going to bother distributing because the whole point here is I'm hoping that that x plus 1 will cancel out because I can't have x plus 1 in the denominator if I want to be able to substitute. And in fact, that is what happens because I get x plus 1 in the numerator over x plus 1 times the square root of x plus 2 plus 1. Given that my numerator will cancel, I'm now definitely not going to have an indeterminate form because the numerator is 1. So in other words, my original limit is equal to the limit as x approaches -1 of 1 over square root of x plus 2 plus 1. These two fractions are equivalent, but the nice thing is that in this new fraction, I don't have the same non-permissible value. So I can actually now just substitute in 1. So this is 1 over the square root of 1 plus 2. Oops, -1 plus 2. Substituting in -1 plus 1, which is 1 over the square root of 1, which is just 1. 1 plus 1 is 2. So this limit is equal to 1/2. So the algebra that you have learned previously includes things like factoring, rationalizing, any other kinds of manipulation. Those are going to come into play in trying to rearrange or find alternate forms of the expressions that we give you so that you can actually figure out what the limit is. That doesn't mean that I can, in the original, if I had had the original function y equals the square root of x plus 2 minus 1 over x plus 1, -1 is still a non-permissible value. But this manipulation allows me to figure out what the graph is doing near -1 so that I can maybe sketch it a little better. And the other type of limit that we often have to deal with is limits at infinity. So what happens as x goes to infinity or as x goes to -infinity? Now, this is a different kind of indeterminate form because if I were to substitute in an infinitely large number for x, I would get an infinitely large number in the numerator and an infinitely large number in the denominator. An infinitely large number plus 2 is still infinite. An infinitely large number times 2 plus 3 is definitely still infinite. So this is an indeterminate form, but that doesn't mean that the limit doesn't exist because an infinitely large number divided by an infinitely large number may have a finite ratio, finite relationship between them. So the formal manipulation that we do here, informally, the leading coefficient is the one that matters the most. An infinitely large number plus 2, the 2 is kind of irrelevant. 100 googolplex plus 2 is still basically 100 googolplex. What matters most is the coefficient of that x. So in the denominator where I'm multiplying by 2, that actually does have an impact, whereas adding the 3 is kind of irrelevant. But algebraically, how we can show that this is true is by dividing by the largest power of x. So in other words, I am going to change this to the equivalent fraction of 1 plus 2 over x over 2 plus 3 over x. The reason this is helpful is I can now consider each part of this individually. So the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 2 over x over the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 3 over x. Where I have a constant, the limit as x approaches infinity just is the constant. So 1 and 2, doesn't matter what x is, there is no x in that expression. If I think about what's happening for 2 over x and 3 over x, as x gets infinitely large, I'm ending up with something like 2 divided by an infinitely large number or 3 divided by an infinitely large number. It's relevant that they're positive. In this case, it wouldn't make a difference if it was positive or negative, but in some cases it does. So 2 divided by an infinitely large number is going to be an infinitesimally small number. In other words, a number that is very, very close to 0, but still positive. So this goes to 0, and technically a positive 0. 0 obviously isn't positive, but a number very close to 0 that is still positive. And same with 3 divided by an infinitely large number becomes an infinitesimally small number. In other words, a number that is very close to 0, still slightly positive. So what I essentially end up with is 1 plus 0 over 2 plus 0, which is obviously just 1 over 2. So that is the limit here. So that actually tells me that as this graph is going off towards infinity, the y value, if I were to graph y equals x plus 2 over 2x plus 3, the y value is approaching 1/2. Now, I don't actually know at this point whether it's approaching from below or on top, but it is approaching a horizontal asymptote of y equals 1/2. So that's what infinite limits allow us to do.